quantum mechanics, or QFT. So we are indeed celebrating 100 years of the development of quantum mechanics, which began early in the century. And although Planck's great discovery was based on light, and trying to understand the spectrum of black body radiation, which is, of course, relativistic particle theory in principle. Light, after all, is relativistic. Most of the early work on quantum mechanics was completely non-relativistic, and the idea that light itself could be a quantum phenomena was foreign even to Planck. Einstein, of course, understood that given Planck's discoveries, light had to have properties, some properties of a particle, and he sort of invented the quantum nature of light, the photon. But the big advance happened, non-relativistic description of atoms with Rutherford's discovery of the nucleus and the structure of atoms. And the Bohr model, which was some kind of arbitrary, now we understand semi-classical treatment of hydrogen, was so successful in explaining the periodic table and calculating the Rydberg constant that it set the stage for the emergence of quantum mechanics as we know it. And all of this was non-relativistic. De Broglie suggested that matter, not just light, behaved as waves. Einstein said waves can behave as particles. De Broglie said that particles can behave as waves. And Stern and Gerlach discovered spin, in effect. All the ingredients were there for the emergence of quantum mechanics 100 years ago. And of course, the great advance happened in exactly 100 years ago in 1925 with Heisenberg's invention of matrix mechanics, the existence of non-commuting observables, very strange to classical physicists. And then in the following year, Schrödinger's approach, a wave equation for some kind of wave, and Dirac's understanding of how one could quantize any classical system by replacing Poisson brackets with commutators. And to some extent, by 1927, well, this was refined by Born, Jordan, Heisenberg, and Bohr to understand that quantum mechanics was really a probabilistic theory in which you could calculate probabilities for events. And Pauli put forward the uncertainty principle, the exclusion principle, which essentially was the theoretical discovery of fermions. And all of this was completed in a very short time. So often happens in physics, ideas, experiments build up, and then there's a phase transition to a totally new way of thinking about the universe. 1927, the story was more or less complete. This is the famous Solvay conference of 1927, where all the inventors of quantum mechanics came together, argued, but more or less agreed on the structure of quantum mechanics as we essentially know it today. So we have Planck, Einstein, Bohr, Heisenberg, Dirac, Schrödinger, they're all there in color. The stage was set for relativistic quantum mechanics, of course. These pioneers realized that quantum relativity was essential. One had to make relativistic quantum mechanics. And that was achieved very shortly afterwards by Paul Dirac, who was trying to make relativistic Schrodinger's equation for the electron and avoid negative energy solutions. Instead, he discovered the square root of the Poisson equation, if you want, or which introduced his famous gamma matrices, and he thought would eliminate negative energy solutions. But it was soon realized that the Dirac's equation, which explained the hydrogen atom even better than Bohr, led inevitably to the existence of negative energy states, or with modern interpretation, antiparticles. For every particle with any quantum numbers, there must exist in a relativistic quantum mechanics theory particles with the opposite quantum numbers. He predicted, in effect, the positron, which was discovered only a few years later. That made relativistic quantum mechanics not a one-body problem. You could not write down a theory of an electron in a potential, say the Coulomb potential. Inevitably, once you have relativity and quantum mechanics, there are antiparticles which inevitably are produced, and relativistic quantum mechanics is inevitably a many-body dynamics. But we did possess a classical theory, Maxwell's theory of electrodynamics, which was so dominant in the 19th century, and it was straightforward, following the principles, the new principles of quantum mechanics, to quantize the electromagnetic field. The field became the operator, was now an operator, not a classical observable, and Maxwell's Hamiltonian theory or Lagrangian theory could be quantized directly. And immediately, these young inventors, Heisenberg, Dirac, Pauli, Weisskopf, Jordan, and others, turned to quantize electrodynamics. But there were problems. The problems were really not conceptual, but technical. We're dealing now with a gauge theory, with redundant degrees of freedom. How do you deal with those? There were ultraviolet divergences. Immediately when you started calculating, nobody could deal with those. So although the basic equations and approach to QED, quantum electrodynamics, were set forward by 1932, it still took over 2 decades to truly understand quantum electrodynamics. Fermi, however, immediately tried to apply construct what we would today call an effective field theory. A field theory that could describe the weak, what we call today, the weak interaction that's responsible for beta decay. Very successful, effective field theory, we would say at the time. And Yukawa suggested that perhaps the strong nuclear force could be mediated by a heavy photon. He really thought, he suggested what we call today the pion, the carrier of the nuclear force that between protons and neutrons, which were the only known elementary particles aside from the electron at that time. But he thought the pion would have spin 1, because all carriers of force have spin 1. The only one that was known was the photon. Of course, it turned out to be a pseudoscalar, and its discovery gave a great boost to the idea that you might describe the nuclear force a la Yukawa, or the weak nuclear force a la Fermi, by quantum field theory. Quantum electrodynamics came to its final form after World War II, when experiments began to see deviations from simple Dirac theory of the electron. Quantum fluctuations would change the charge, the magnetic moment of the electron, and experimenters measured these very small effects, stimulating theorists, Feynman, Schwinger, Tomonaga, and Dirac, to finally understand how to do meaningful calculations in quantum electrodynamics. Understanding that what we measure, and therefore must take into account in our equations, and the solutions must account for, are not the parameters that one puts into the theory that describe the mass and the charge at arbitrarily short distances, but what we actually measure, which is always at some finite distance. This is the program of renormalization, which, although they didn't truly understand, allowed them to do calculations without encountering infinities, and to start calculating using a marvelous graphical and conceptual technique that Feynman discovered, Feynman diagrams, and that enables one, as you know, to calculate with incredible precision the quantum corrections to the naive predictions of QED. And as fundamental physicists, we are incredibly proud of tests of our fundamental principles, like the anomalous magnetic moment of the electron, or today of the muon, and other examples of precise calculations where we can measure the anomalous magnetic moment of the electron to 1 part in a trillion, as well as calculate those corrections to the same degree of accuracy. A monumental achievement which has taken many decades, but there is no other place in physics where such incredible accuracy is even pursued, much less achieved. It's really characteristic of fundamental physics that we continue to try to test our theories to better and better accuracy, because we all know that the only judge of the truth of our theories and our understanding is nature. So we continually ask nature, are we right? Are we right? So far, in QED, for example, nature says, so far you're right, do a better experiment. At the same time, with the success of quantum electrodynamics, people tried very hard to extend quantum field theory to the other, much less understood forces in nature, those that act within the nucleus, the weak nuclear force responsible for radioactivity, and the strong nuclear force that holds nucleons together. And many new techniques were developed at that time. Already in the case of quantum electrodynamics, Feynman came up with a reformulation of quantum mechanics, which has motivated us ever since, given us a whole new perspective on quantum mechanics and all of its forms, and provided the basis for many new ways of calculating, where the amplitude for particles to propagate from point x1 to x2 in time t where the amplitude is written as a sum over all possible paths, weighted by a phase, the exponential of I times the action, the classical action of the system under discussion, which probability is the square of that amplitude, and that gives us a whole new way of thinking about quantum mechanics at the conceptual level, as well as the understanding of how semi-classical or the classical world emerges when Planck's constant is small or the action is big as the dominant saddle point in these integrals, these path integrals. Those path integrals, path integrals were have been generalized, of course, to any quantum system, including quantum field theory, where one is now not just integrating over paths, but over fields in an infinite dimensional integral, which our mathematical friends throw up their hands and say, what are you talking about? What the hell is this measure? What does this mean? We still don't really know in most interesting cases. And the true understanding of what integrals like this mean in a rigorous mathematical sense, in some ways, many of us regard as the most important question that our mathematical friends could answer. It's one of the Clay Millennium Prizes and probably the hardest for a theory, which I will certainly come to. So over the years of the 60s, 50s, people tried to develop tools for dealing especially with a strong nuclear force. There was no classical theory to quantize, and there was no obvious theory. In the spirit of physics, some people decided to concentrate not on the dynamics, but on the observables, to try to construct a theory based on the observables. The observables we have for relativistic quantum mechanics are largely restricted to S-matrix elements. The unitary many-body particle Hilbert space of operator that describes the amplitude for two particles which are collided, say at CERN, boom, and produce many outgoing particles. The amplitudes for those processes, which is what our experimental friends measure, are the basic observables. And already early on, the 40s, 50s, Wheeler and Heisenberg said one should focus on these and not try to invent a classical theory and quantize. This, of course, is what our experimental colleagues at, it's a picture of course, the accelerator at CERN, the kind of modern detectors. Conceptually, all of these are just fancy modern successors to Rutherford's famous experiment in which he figured out the structure of the atom. These, of course, use bigger, more energetic collisions and much fancier detectors, but they discovered the Higgs eventually. So in the 50s and 1960s, there were many important theoretical developments in our understanding of quantum field theory, the quantum theory of fields. One important development was the connection between quantum field theory and statistical mechanics, which is kind of based on the simple idea that if you consider quantum field theory not in a background space-time, a Lorentzian background space-time, but in a Euclidean background space-time, where time is imaginary and periodic. So if you want a cylinder in time, then the time evolution operator, as t is replaced by I beta, and beta is periodic, looks like replacing the time evolution operator with a Boltzmann weight. And a integral over paths in Lorentzian space, when continued in this way, on a periodic imaginary time, looks like the same as calculating the partition function of a system at fixed temperature. So there's an analytic continuation, if you want, between quantum field theory in D, spatial and one time direction, and thermodynamics in d spatial dimensions. This is incredibly rich correspondence that has greatly informed both thermodynamics, system mechanics, and quantum field theory, and led to an incredibly useful over many years between people who do, say, high energy particle physics and condensed matter physicists who are interested in the thermodynamic properties of macroscopic quantum systems. The renormalization group was invented towards the end of the 60s as a tool to understand quantum field theory as well as phase transitions with remarkable success. Conformal field theory, which describes often the nature of quantum systems at values of parameters or temperature which undergo a continuous phase transition, was developed and with great success by Wilson and others, and has had enormous impact on relativistic quantum mechanics as well. One of the important developments, in retrospect, of course, is the generalization of Maxwell's theory and an abelian gauge theory of electrodynamics to non-abelian gauge theories, which Yang and Mills did already in 1954. This generalization was immediately tried by many people to be applied to quantum field theory of the quantum version of this non-abelian gauge theory to just understand the ill-understood, totally ill-understood nuclear forces. But the problems were immediate. They were known, for example, to Pauli, who supposedly had done this mathematical generalization on his own and realized that it implied that the photons, the charge carriers, the carriers of the non-abelian charge of such a quantized theory would be massless, like the photon. And since there were no other massless spin 1 particles ever observed, such theories had no application. So he never published his results. But when Yang gave a talk at the Institute describing this work, Pauli would barely let him talk. All other attempts to apply these ideas to particle physics, to fundamental forces in the beginning, in the 50s, early 60s, failed. Because in the case of the weak interactions, where it was by then natural to understand that these forces were sort of vector-like, chirally vector-like, the symmetry is clearly broken, and it was evident to many, including Pauli, I think, that it is simply inconsistent to gauge a broken symmetry in the obvious way. This was solved in the early 60s by Higgs and Broughton Anglaire and others. The mechanism of breaking the symmetry, a phenomenon which is pervasive throughout all of physics, almost all symmetries, beyond the space-time symmetries that were emphasized by Einstein and others, are broken symmetries, and magnetism, for example. But in the case of a gauge theory, the broken symmetries, the spontaneous symmetry breaking, in other words, the discovery that the system has a vacuum, a stable vacuum, which is asymmetric, like in this kind of potential, break the symmetry and give the gauge bosons a mass. And therefore, they're not excluded by experiment. They simply might be too heavy ever to be observed. This, of course, was the basis of the gauge theory, the SU2 cross U1 gauge theory of electromagnetism and the weak interactions of Weinberg, Glashow, and Salam, and others, which turns out to be correct and is an essential part of the standard model, which has now been verified by the discovery of the Higgs to some extent. Strong interaction was much harder. There was no understanding of the strong interaction. There were many new particles being discovered all the time. It was not clear which was elementary, what was the theory. There was no classical theory. The coupling, the interaction was very strong, so there were no methods to calculate, even if one had a theory. Couldn't use perturbation theory. And famously, the discovery that really broke the ground, which I unfortunately can't describe in detail, was an experimental discovery at SLAC of using electrons to probe the structure of protons, much as Rutherford used alpha particles to probe the structure of atoms, and discovered that it looked like protons were made out of point-like particles that looked like they were not interacting at all at very short distances over very short times. That was really astounding, and certainly had a big influence on me. I'd been working on ways to test the nature of the proton by using these deep inelastic scattering experiments, and the results convinced me that proton was made out of quarks. The various sum rules that we derived that indicated the protons indeed, that the charged constituents of the proton looked in all senses like quarks. And yet quarks, we've never seen a quark, so what if they were interacting weakly, how come you couldn't pull them out of the nucleus? And of course the answer turned out to be, again, non-abelian gauge theories, where the sources of the gauge fields are three instead of one, electromagnetism, two in the case of weak interaction. Now we have three colors and anti-colors. And such a force, as it remarkably turned out, although it would be Coulomb-like in classical gauge theory, in the presence of the quantum vacuum populated not just by electron-positron pairs, but also by quarks, which are charged and affect this paramagnetic, as it turns out, medium, actually force the flux, the field lines of the chromodynamic field to be squeezed as much as possible into a flux tube. And such a flux tube behaves very much like a string, constant tension, which means the force between a colored quark and an anti-quark never decreases, and that not only explained, remarkably, the fact that the quarks interact very weakly at short distances, but also that they can't be pulled apart at large distances. That led immediately to the theory, quantum chromodynamics. This is actually what it looks like if you solve the equations using lattice gauge theory, and you have heavy quarks, pull them apart. You see the flux is contained in this tube, and in fact, in terms of a potential, the potential does not saturate its linear potential, which confines the quarks. This theory has now, 50 years later, been tested literally thousands of times with accuracy exceeding 1% in every possible. This is my favorite picture of the decrease of the strong interaction, coupling, the strength of the interaction as a function of distance. So this is large distance, this is short distance. This is actually not the most up-to-date picture, but it's the same. It's now well tested in literally hundreds of experiments to a level of about 1% or less. It's also an amazing theory. I like to boast about it. I call it a perfect theory, at least by the standards of the past. Most theories have infinity somewhere. Electrodynamics, if you go to very short distances, everything blows up. And actually, we believe that electrodynamics, and hopefully our mathematical friends will prove it, they have for simpler theories of this type, that such a theory is inconsistent. The only sensible theory of quantum electrodynamics, a U1 gauge theory with one charged particle, is a theory where the charge is zero, where there's no coupling. Note in QCD. QCD, the bare coupling, the coupling at short distances is zero. And it grows, but it saturates at some point. The quarks pull themselves together. There's no longer any force. So, no problem. Also, because the force gets weaker at higher energies or shorter distances, this is a theory, unlike any other theory we've ever had, which has no place where it breaks down. You go to higher energy, shorter distances, theory becomes trivial. By itself, it would be totally complete. It also, in a sense, has no adjustable parameters, and that's really remarkable. The goal of physics is to come up with a theory or a set of ideas where everything is fixed. And that, to some extent, is true in QCD, except for those quark masses. Quarks have masses, and QCD says nothing about those. Those have to be measured and put into the theory, but they play a very small role. At least the light quarks are so light you can almost neglect their mass. And then everything is calculable. All dimensional parameters, like the ratio of all masses, can be calculated. Now, of course, there are other aspects of the theory that we don't understand, the quark masses and the mixing, and why are there 3 colors and not 27? And then, of course, there are other forces in nature, like gravity especially. But these features of the theory are truly novel and amazing. How can you calculate in such a theory with very strong forces? Well, the only tool we have at the moment for precise, controllable first principles calculation is lattice gauge theory, where one replaces those infinite dimensional integrals by finite, large dimensional integrals, and take the limit as the lattice spacing goes to 0. And that has reached a new level of maturity using both the fact that computers are getting better and better every year, and theorists are getting smarter and smarter every year. And over the last 40 years, these calculations have achieved an incredible ability to calculate the static properties like the masses and, for example, of strongly interacting particles, which now can be calculated to incredible accuracy, better than 1%. The mass of the proton, the mass of the neutron, and the mass difference, the small mass difference of the proton and the neutron, and every particle that has been discovered. That, however, good lesson for us, has taken 40 years. And it's required 2 things. It's which required an improvement in the power of computing power by a factor of 1 billion. That's Moore's law acting over 40 years. But it also required an improvement of 1 billion in theoretical ingenuity, algorithms, finite size effects, chiral symmetry breaking. Together, that's a factor of 10 to the 18, and that was required. So these gauge theories of the strong and the weak, and of course the electromagnetic interaction constitute, together with the experimental discovery of all these particles, the quarks in 3 families and their lepton friends, the electron and neutrinos, together in what I would prefer to call the standard theory, describing the 3 forces of nature, the 3 gauge groups, the 3 charges, the 1, 2, and 3 charges, and the masses of these elementary constituents determined by the Higgs mechanism. Higgs mechanism doesn't determine the mass of the proton. That's the energy of the confined quarks and gluons. And without the Higgs, you'd still have the proton and its mass. But it does describe the mass of the elementary leptons and quarks, these fermions. And it seems to work, it could work, from the highest possible energy that we can conceive of without gravity, the Planck length, to the size of the universe. We know of no limitation. There's much about this standard theory model that is not explained by the standard model so far, but mostly having to do with the Higgs sector, the masses of the quarks and their mixings. This is a remarkably already unified picture. It's all gauge theories, 1 charge, 2 charges, 3 charges. They fit, everything fits together beautifully. And so naturally, we have been trying to unify. But just the existence of this standard theory has had enormous implications for other areas of physics, especially the early universe. So at the same time the standard model is being completed, astronomers, with the discovery of the CMB radiation, were beginning to attempt to understand the history of the universe. And although it's hard directly to see the very early universe, theoretically we can, because we have this theory, which gets simpler and simpler as you go to higher and higher energies, temperatures, density in the early universe. And so interesting things happen. We predict and study and look for experimental signatures, for example, the various phase transitions. In the case of quantum chromodynamics, between nuclei, confined quarks, but as you heat them up, these nuclei, we predict, melt into unconfined quarks and gluons. That can be explored on Earth, and we try to study the phase diagram of quark-gluon matter, for example, at ALICE, at CERN, and Brookhaven, and it's absolutely fascinating, but I don't have time. So what have we learned, very conceptually, big picture from the standard model? Well, we've learned that matter is made out of charged spin 1/2 fermions, quarks and leptons. We've learned that the forces are described by quantum gauge field theories. And they come in 3 phases. 3 kinds, 3 phases. Maxwell's theory, 1 charge, has in the Coulomb phase, the force is long range, 1/r², everything you learned in high school. The electroweak theory, SU2 gauge theory, 2 charges, flavor, up, down, charm, strange, exists in another phase because of the Higgs mechanism. It's screened. The force is screened. The gauge bosons W and Z are massive. And this Higgs mechanism is generated by what so far looks like a elementary scalar field theory, but somewhat unnatural. And one of the main experimental theoretical goals of the next decades is to truly understand in a fundamental way whether this simple picture is correct and why and how. And finally, the strong interactions, 3 charges, color, which exist in a confined phase, where the forces are confined. You cannot separate the quarks or the gluons. That's the standard model. Beyond the standard model, well, it's pretty complete, amazingly successful. But there are many indications from experiment and theory that there's much physics not understood beyond the standard model. Neutrinos have mass. That's easy to correct, but we don't even know whether the neutrino is its own antiparticle, a scandal, actually, of current high energy physics that we haven't answered that question over all these decades. Baryon, a lot of baryons in the world, very few antibaryons. We can understand how that can happen, but we're not sure exactly how. The universe, astronomers tell us, mostly consists of dark matter as far as the matter content. Astronomers see it through its gravitational effects and map out its distribution in the galaxy and in the universe, but we've never observed it on Earth directly or produced it in accelerators. That is the biggest experimental challenge we face. I would have been absolutely sure that this would have been discovered 10 years ago. It's really surprising that we haven't yet understood the nature of dark matter, but we will. It's out there. We can see it. We can measure it. So we will learn what it is. Then there's dark energy, or cosmic acceleration, which is a different kind of problem associated with gravity, but there's many, many open questions about the cosmological constant that might explain it. Is it constant, really? Is it decaying, etc.? What is the fate of the universe? From a theoretical point of view, we're driven towards unifying these forces that are so similar and particles that fit together so neatly. The nature of the Higgs mechanism is still bizarre and ill understood. The whole system of flavor masses and masses of these quarks, which can differ by 9 orders of magnitude, we have no idea where that comes from. Why are there 3 families, generations? And then, of course, now with the connection with astrophysics and cosmology, there are many, many important theoretical questions that require gravitational and particle physics input. So they're going to be answered, of course, the usual way by both experiment and theory. Theory, is easy to imagine all sorts of solutions. Experiment today is much harder. But there are plans, beautiful plans, being put forward throughout the world to go one step beyond our current exploration by an order of magnitude at least. One of the leading contenders, of course, is CERN's plans for the future beyond the LHC of constructing a 100-kilometer tunnel that could be used for both E+, E- collisions and eventually in the future for proton collisions. There's a similar proposal here in China, CEPC, which intends to build a large tunnel and do E+, E- experiments, which are critical at the moment to explore this Higgs sector. And then eventually such a tunnel could be used to collide protons. That's a very exciting development, which I have been slightly involved with over the last 20 years, led by Yifeng Wang here. And I fervently hope for the good of China, for the good of science, for the good of the world, that this project is approved. It's an incredibly realistic and wonderful project in its late stages, All it needs is approval. If anyone's listening, please approve. So, from a theorist point of view, the question that one of the most important questions is, how do the forces unify? Right after the Standard Model was developed, you could extrapolate the theory. Strong force got weaker, the electromagnetic force got stronger. Just using simple theory gets simpler and simpler as you go to higher energies, so extrapolation becomes simpler. And it was discovered that the forces kind of come together at a very high energy, very close to where gravity becomes a strong quantum force. The so-called Planck length that Planck understood over 100 years ago when he realized he had to introduce a fundamental unit of action. And together with the velocity of light and Newton's constant, you have all the dimensional parameters you need to characterize all physical observables. The weird thing, of course, is the Planck length is so small, 10 to the minus 33 centimeters, energies are so high, there's no way we can directly probe such distances or energies. But theorists can. And if gravity is becoming essential, we must start treating gravity quantum mechanically. And attempts to do that, by the way, and attempts were tried immediately after the development of quantum mechanics. And I understand that one of the reasons Einstein was so opposed to quantum mechanics was that nobody ever came up with a quantum theory of his theory of gravity. And all attempts failed because gravity is the dynamics of the space-time metric, of space-time itself. And the quantum fluctuations of space and time, when they become very strong, sort of space looks like this, or space-time, and everything breaks down. Uncontrollable fluctuations, which kind of informs us that we have to go beyond Einstein's theory. And luckily, we had string theory. String theory naturally turns out to be able to unify gauge forces that underlie the Standard Model and gravity in a totally natural way. In fact, one can't avoid gravity if one, in string theory. In fact, string theory came from particle theory, from the attempt to understand the forces between quarks, understand the phenomena of strong interactions. Now we understand that a meson, for example, has this flux tube, looks like a fat string, but string-like behavior was deduced from observation of scattering amplitudes of protons and neutrons around towards the end of the 80s, and that's how string theory emerged. So in string theory, these flux tubes are really strings with quarks attached at the end. And more we understand in a deep way that gauge theories and string theories are different ways often of looking at exactly the same physical phenomena. In string theory, these open strings, flux tubes, mesons, you can close the strings. In fact, you have to close the strings for mathematical consistency. And once you do that, you get a sector with no charges at the end, a neutral sector, a universal sector, which turns out to be gravity. Can't avoid it. You want to describe mesons, you have to describe gravity. When people were trying to describe mesons in this way, that was regarded as a problem. It then became a virtue and a possibility of unification. Are, in some sense, all particles different vibrations of a superstring? It definitely could be. In fact, it's really the only comprehensive, well-formulated, well-based attempt so far at such a unification. Now, in recent years, this kind of duality between different ways describing the same physics has exploded. Not just open and closed strings, but quantum field theory in Minkowski space, in our approximate space-time, and strings in a background space-time which has a well-defined boundary, like anti-de Sitter space, turn out to be remarkably the same theory, different dual descriptions of the same theory. This gives us, for the first time, in a very limited sense, a way of actually defining string theory non-perturbatively. It's simply quantum gauge theory in Minkowski space. So this has totally dominated string theory and fundamental theory and quantum gravity for the last 30 years. Enormously powerful tool. It's resolved one of the mysteries of quantum gravity that was realized by Hawking in his study of black holes. If you drop quantum systems, any system, into a black hole, you seem to lose information. You can't see what happens in the black hole. But he discovered that black holes radiate and disappear eventually. What happens to the information? That has driven enormous theoretical work by relativists and quantum field theorists and string theorists for the last almost 50 years, and has recently been resolved in many ways by string theory. Is information lost? Well, these black hole paradoxes can be formulated in these cases where we have this exact, we believe, exact. Physicists say exact. It would take 400 years for this to be rigorously proved mathematically. Say ADS-CFT between a well-understood, quote-unquote, quantum field theory cousin of QCD, supersymmetric cousin of QCD in just in 4 dimensions, and quantum string theory in ADS space times a sphere. So Hawking claimed that black hole formation evaporation violates quantum mechanics, but we can set up a system which is a quantum mechanical system with no space, no gravity, or reduced space, but no fluctuating gravity, a fixed space-time, and quantum gravity in a bigger space-time. For example, a black hole in ADS5 is dual to a quark-gluon fireball in this SUN supersymmetric quantum field theory in Minkowski space. These theories we understand, the gauge theories, and they are definitely unitary theories which do not lose information. They're dual to black holes. This encouraged Hawking to give up. He agreed. No information lost. But today, with much more work, beautiful work in the last few years especially, we understand in much more detail how the information is not lost. Much more work remains to be done. This and many other indications are that space-time is emergent. This duality is between theories and totally different space-times. Much of space is kind of emergent in those dual descriptions. That means gravity, of course, is dynamical space-time. We have many, many examples now where some or all of space emerges, can be thought of as emergent. And this duality, this kind of emergent is really novel and fascinating, and one of the main subjects of current present research. Geometry, in some sense, is dual to the entanglement structure of the quantum dual state, which is non-gravitational. We don't really have any good example of the emergence of time. That's really conceptually hard to imagine. And then, where time is crucial, is the history of the universe. the universe, when we are trying to solve a theory which contains gravity, especially quantum gravity, we're trying to construct a theory of the universe, the whole space-time manifold. The universe is the history of space-time, the history of space, if you want. And that includes understanding the beginning and the boundary, if there is a boundary, and the end. And we simply have never had to encounter such a problem in physics before. What determines the initial conditions? That's something physics has never addressed. But if you're trying to solve a unified theory of gravity and all the other forces, that's what you need to do. And we don't even know whether physics is capable of it. We don't have any example of that. There are proposals, Hartle-Hawking universe, etc., things like that. But in our current theories, everything breaks down at the beginning. So we don't know really what we're doing. If space-time were to be emergent, if we could understand the beginning of the universe, say, or more generally, is quantum mechanics ever going to be modified? This has been tried forever. And the answer is, of course. To some extent, as physicists, we know from our history that every concept we have will be modified. That's at least been true until now. I'm sure it will be true in the future, but how? Every attempt of quantum mechanics for the last 100 years that has been tried is not consistent with experiment and or logic. But if space-time is emergent, quantum mechanics at the very least will look very different. What we mean by physics will look very different. Typically, what we mean by physics is we set up some experiment, initial condition, we make predictions about observations in the future. But if time, in some sense, is emergent, as it more and more appears to be, I have no doubt that quantum mechanics, in some sense, will look and be very different. So what is the current framework of theoretical physics? We don't know. It is some incredible framework that includes strings, branes, all consistent quantum field theories, and quantum gravity. They all are related, connected. But the total framework, we don't know. Quantum field theory, until recently, was sort of the framework that gave rise to the standard model. String theory at first seemed to be different, but now we know they're really the same in some dual fashion. Quantum field theory is a framework. It's not a theory. You don't test quantum field theory. You test the standard model. And there are many standard theories, different quark masses, whatever. There are many theories in this framework. String theory originally seemed to be special. It had no dynamical parameters. It might be unique in some sense. But even though all the parameters in our perturbative semi-classical construction of string theories, there are millions, in fact, an infinite number of string theory vacua in these solutions. So, no parameters you have to put into the theory, but an infinite number or enormous number of possible vacua, just as bad. So I like to think about theory space, the space of all theories in a given framework. What are special in quantum field theories, which we barely understand, are conformal field theories. I'm not going to describe what they are, but they are special points which are under incredibly more precise mathematical control. If mathematicians want to actually prove the existence of quantum field theories in a rigorous way, obviously CFTs are where to begin. They can be perturbed. Conformal field theories have no scale. The world has many scales, but these theories can be perturbed, and for large distances, you can control those perturbations. You can try to perturb them by so-called irrelevant operators, which become important at short distances. Those are much less well understood. There are a finite number of relevant perturbations, an infinite number of irrelevant perturbations, and they usually end up in meaningless theories. Some irrelevant perturbations are much more interesting. String theory could be thought of as an irrelevant perturbation of quantum field theory. But I suspect that this theory space that we know about today is perhaps just a small part of the space of all possible consistent quantum theories. We simply don't know. We don't know whether string theory is just a lucky example of a UV complete theory or not. So in a fundamental sense, the future of quantum field theory is unknown. We don't know where it sits in the space of all theories. And the final goal, of course, would be a unified framework that consists of all consistent, at all scales, quantum theories, relativistic quantum theories, and even better, a unified theory. What particular theory of that framework is the real natural world? Particle physics, this is the problem of unification of all standard model of gravity. Uniqueness, what picks the particular standard model out of this big framework? Oops. And it's telling me I have to go, which is true. But I'm almost at the end. What picks the theory? The other big problem conceptually is the cosmology, as I indicated. How did the universe begin? Now, I believe these are connected. String theory has 10 to the 500 vacua, but none of them look like the real world in the sense that any of them which breaks enough of the symmetry to look like the real world at the beginning makes no sense. None of them, all of them encounter complete breakdown at the Big Bang. It could be that in a more unified way, what picks the unique theory, like the standard model, from the framework, like quantum field theory, is the fact that these theories must have a consistent description of space and time from the beginning to the end. So they're connected. And obviously connected with the nature of space and time, which is probably necessary to understand to begin to answer these questions. So there we are. These are difficult problems. Now mostly, these fundamental problems are mostly explored theoretically. And there I always remind myself of Einstein's encouragement and warning: the successful attempt to derive delicate laws of nature along a purely mental path, which is what theorists often do, by following a belief in the formal unity of the structure of reality, all fits together and makes sense, encourages continuation in this speculative direction, the dangers of which everyone vividly must keep in mind who dares to follow it. So I'm optimistic. I truly believe that once a fundamental question becomes a well-formulated scientific question, like the beginning of the universe, which has only become well-formulated, addressable by experiment, observation, and mathematical model recently, it will be answered in your lifetime. Probably not mine, but many of you. So keep going. Thank you.
Okay. Well, thank you very much, David. I think you have given a spectacular lecture about the deep achievement of modern physics leading to the understanding of nature. And we hope we can continue in the future. Thank you for the spectacular lecture. Okay. David has to go to the airport now, so we could not have any questions.
The next lecture is about to start. Please be seated. Okay, the next lecture is about to start. Can you please, if you are attending the next lecture, please be seated. It is starting in 1 minute.
Please sit down immediately.
Ask you to try your voice.
1, 2,
1, 2, 3.
3.
Okay. Well, as most people would agree, one of the greatest achievements of mankind was the building up of the Standard Model in theoretical physics. We just listened to one of the founder on theory by David Gross. But now, without experiment, there could not be any interest in theory. And the leading experimentalist in the last 50 years is Professor Sam Ting. And he's going to give a talk about what he did in the November evolution and 50 years of electrons and positron physics. Thank you.
Since everybody's informal, I will be also informal. It's okay. I take out my jacket. Yeah. You can give to the lady there. Professor Yao, Professor Yifan Wang, ladies and gentlemen, I am an experimental physicist. At university, I studied both math. I have 2 degrees, one in mathematics, one in physics. Finally, I decided my ability is very limited. I better stay with experimental physics. So what I want to do today, to share with you half a century of experience in particle physics, working in accelerators on the ground, at Daisy, at Brookhaven, at CERN, and on the International Space Station. It has been 50 years since the discovery of a new form of matter. This is a New York Times front page, long front page article on November 17th, 1974. New and surprising type of atomic particle form. So this is the result of a series of experiments. The first experiment is measuring the size of the electron. Modern electromagnetic theory, QED, requires that electrons have no measurable radius. That's by Feynman, Schwinger, Tomanaka in 1948. The experiment all agreed well with all, the theory agreed well with all experiments until a 6 billion electron accelerator, Cambridge Electron Accelerator, CEA, produced a more sensitive measurement of size of the electron. So this is the CEA accelerator, has 300 meters, and with the electron inside, that was the highest energy accelerator in the world 50 years ago. It produced 6 billion electron volt light, and on a target, you look the size of the electron. What they found is from the measurement, compared with the model of the electron, zero radius, there's a deviation at a distance of 10 to the minus 17 centimeter. So the electron has a radius of 10 to the minus 17 centimeter. And this experiment was quickly confirmed by subsequent experiment at Cornell. So 2 experiments show the same result, and people become very excited in international conferences. This is one of the main research topics. Due to the importance of the results, I decided to redo the experiment with a different method at the German accelerator in Hamburg, Germany. And so this is at that time, very small accelerator complex, and this is my team of few people. Unexpectedly, we found light rays, massive light rays. We found when you have a light ray on a nuclear target, you measure QED, it's completely agreement with the QED. Namely, the electron has no radius. But then we found at a mass of 3 particles, one called rho, another called omega, and another called phi, you have a deviation from QED. This is not because the violation of QED, but because a photon suddenly changed to a massive particle with same quantum number, go back to the electron positron. So it's the discovery that light ray and light ray with mass have the same properties. So the second series of experiments concerned light rays and massive light rays. At that time, there were 3, rho, which is a 2-pi resonance, omega, a 3-pi resonance, and phi, 2K resonance. All of them have a mass about the proton mass. So light ray, a massive light ray, should therefore be transferred into each other. That is the theory. The question is, do they actually transfer into each other? So a large group of experiments were carried out. The most interesting one is the observation of forbidden decay. Omega is a 3-pi resonance. A 3-pi resonance does not go to 2-pi. So you cannot have a final state of 3-pi and 2-pi interfere. But the omega can go to a light ray. Light ray can go to 2-pi. And so there's a very finite chance omega will go to 2-pi. And this was looked by Sternberger and by Glashow, by many, many famous physicists. Never found it. With the precision detector, we indeed found, when you measure the pi plus, pi minus spectrum, it is not only rho alone, but the rho omega interference. The third experiment is a discovery of J particle. We learned that photons and massive photons do transform into each other. The question is, why should there only be 3 heavy photons? All have a mass of 1 GeV. Rho has a mass 760, omega has a mass 780, phi have a mass 1 GeV. Why there are no more heavy ones? To go to higher mass, we move to higher energy accelerator. So this is the proposal I made to Brookhaven National Laboratory. Said the best way to search for vector meson is through production experiment of the type proton-proton, go to vector meson, go to E plus E minus. That's because vector meson are produced by strong interaction, thus a high production cross-section. Second, one can use high intensity, high duty cycle extracted beam. Namely, you can take all the accelerator beam out of the accelerator and put it on your target. And third is the E plus E minus enhancement limits the quantum number to 1 minus, thus enabling us to avoid measurement of angular distribution of decay particles. I stated very clearly, contrary to popular belief, the E plus E minus storage room is not the best place to look for vector mesons. In the E plus E minus storage room, the energy is well defined. A systematic search for heavy meson requires continuous variation and monitoring of energy of the two colliding beams. A difficult task requires almost infinite machine time. Storage ring is best suited to perform detailed study of vector meson parameters once they've been found. So in a Brookhaven experiment, we take 10 to the 12 protons per second from the accelerator on 10% beryllium target. At that energy, the multiplicity is 10, so you have 10 to the 12 particles per second produced. 10 to the 12 is a high number, it's a very large number. After 10 to the 12, the rarest of them all is the E plus E minus pair, which is 1 in 100 million of pi pair. Therefore, if you want a 1% experiment, you need a rejection of 1 part in 10 to the 10. What is 1 part in 10 to the 10? During a rainstorm over Beijing, there are 10 billion raindrops per second to find out which drop is red. Therefore, it's a quite difficult, almost impossible experiment. The experiment was not popular with physics community. Most of the physicists believe the search for heavy mesons was not the most interesting research topic. Few believe such difficult experiment could be carried out successfully. So the proposal was rejected by most of the laboratory. I remember talking to Daisy, talking to Fermilab, talking to CERN, and finally the proposal was accepted by Brookhaven National Laboratory. So this is an area view of the detector. Because you have 10 to the 12 particles, so to shield the detector, you need 10,000 tons of concrete, 5 tons of uranium, 100 tons of lead, and 5 tons of soap. 5 tons of soap is to stop soft neutron. I did have some trouble with the government to buy 5 tons of soap, but finally MIT decided to buy it for me. So we developed many very precise detectors, and this is a position detector developed by the late Ulrich Becker of MIT. To sort out multiple tracks, you put the proportional wires at 60 degrees apart. Well, 60 degrees apart, You have A1 plus A2 plus A3 equal to B1 plus B2, B3. Therefore, you have a rate of 20 megahertz per second. And when the experiment is over, one of the chambers was put at the Smithsonian Institute in Washington for many years. In the early summer of '74, we took some data in high mass Beijing 4 to 5 GeV. However, analysis data show there are very few electron positron pairs. By the end of August, we tuned the magnet to accept effective mass of 2.5 to 4 GeV. Immediately, we saw clean, real electron pairs. But most surprising of all, most of the electron positron pair peaked narrowly at 3.1 billion electron volts. A more detailed analysis showed the width is less than 5 MeV. So this was the first data showing an expected peak at 3.1 GeV taken in August 1974. This is an experiment extremely difficult with an enormous amount of background. How do you know it's not due to instrumentation bias? The way to do that is to lower the magnet by 10%. If once you lower the magnet by 10%, the particle bends to a different part of the detector. If the peak is fake, it will shift away, but it did not. So the discovery is verified. So on the left, show the graph. The blue area is the spectrum with 100% of magnetic field, and the pink area is when you lower the magnetic field by 10%. The unique property of the J particle is its lifetime is 10,000 times longer than other particles. The significance of this is similar to suddenly discovered in a remote village on Earth, a village where people live to be instead of 100 years to about 1 million years old. And that's why they're quite different. And second, the spectrum is similar to that of positonium. On the left is the spectrum of positonium, on the right is the J-side particle transitions. On November 11th, I telephoned Giorgio Ballattini, a close friend before, the director of Frascati Laboratory in Rome, informed him of his results. So the so-called November Revolution has 3 publications in physical review letters. One submitted November 12th by us, another a day later by Professor Richter's group, another by Ballattini's group in Italy, November 18th. It shows once you know where to look, you can get there quickly. So this is our group, by modern standard, is a rather small group. The discovery of J particle confirmed the existence of charm core predicted by Glashow, Laplace, and Mayan, which stated in October 1970, the model featured remarkable symmetry between lepton quarks. Let me just mention, during the summer when I was doing the experiment, the 3 people, 2 of them come to visit me often and try to convince me the experiment is not worth doing. I received a notice of obtain a Nobel Prize on October 18th, 76. A few days later, I got a telegram. I got a mini telegram. The most notable one is from Richard Feynman, whom I got to know quite well. The telegram said, "Congratulations, son. But why do they give prize to guys who discover things that I don't expect and didn't understand? Please don't let the prize go to your head." Meaning, okay, you're getting a Nobel Prize, it's because you have made a contribution in a specific field. Does not make you an expert on everything. This is one of the main reasons I never sign any petitions or public issues which I'm not qualified to understand. So in December 10th, 1976, in Stockholm, I received the Nobel Prize, and looking at the diploma of my two daughters. From academician Yifan Wang, I learned tremendous progress in the United States, in China, in Russia, in Germany, and try to study tau charm factories. And this is the luminosity as function here. The highest energy is BEP C2 in Beijing. From Professor Wang, I obtained this graph, the spectroscopy of Beijing spectrometer. When you have 58 million events, you see the graph on the left, and when you become 225 million events, you begin to see the structure. Once you have 10 billion events, you see clearly the structure. And that's really a very nice graph. So up to now, in Beijing, 30 new hadron is discovered at best rate from Chang based on production and decays. The fourth experiment is the electron at higher energies at the 46 billion electron volt collider in Hamburg with the positron and electron collision. And this is the beginning of international collaboration in high-energy physics for me. The experiment is called the Mark J experiment. Let me also take this opportunity to acknowledge that we have 5 decades of collaboration with Chinese scientists. After the Cultural Revolution in August 1977, Chairman Deng Xiaoping suggested sending 10 scientists each year to collaborate with me. Since then, many Chinese joined my team, have made contributions were recognized worldwide. And this is the first arrival of the first team of Chinese to the Mark J experiment in Hamburg. At the same time, there's the development of the electroweak theory when the accelerator was built. The first paper, 1960, followed by second paper, Steve Weinberg, and then a final paper by Abdul Salam. In Glasshow's paper, he stated, the simplest partially symmetric model reproducing observed electromagnetic and wake interaction leptons require the existence of at least 4 vacuum boson fields, including the photons. Namely, there should be intermediate vector boson. At that time, it's just a theory, not much people paid attention. Mark J experiment, as announced by Physics Today, confirmed the interference standard model by measuring the electron positron to mu plus mu minus. If there's a virtual intermediate vector boson, it decays to mu plus mu minus, and this will introduce a forward-backward symmetry or measurement as function of theta, shown here, agrees with electroweak theory, no longer agree with quantum electrodynamics. Also, an important thing is discovery of gluon at Beijing, Germany. When you have an electron-positron collide, you produce antiquark, quark, and gluon. With the increase in gluon energy, you begin to have from 2 jet given to 3 jet divided. And this was announced in the front page of the New York Times as a totally unexpected discovery. And also was announced in the People's Daily in September 5th. Professor H.S. Chen, my former collaborator, recorded this incident and the history because with time, different people sometimes have different memories. The 5th experiment is the electron-positron physics at the highest energy. There are 3 experiments at CERN, which lasted 21 years, with 100 GeV positron collide with 100 GeV electron. And this accelerator have a conference. Circumference of 27 kilometers. The temperature when the particle collide is about 400 billion times higher than the surface of the sun. And so equivalent to the temperature of the Big Bang origin of the universe within 10 to the minus 11 seconds. So this is a large international collaboration. First time I'm involved in this. I'm from Korea, from China, including Taiwan, including Pakistan, India, most of the countries, United States, and many universities in Europe. So this is a cross-section of the experiment. And the magnet is 10,000 tons, and it contains 300 tons, 100,000 channel uranium calorimeter. Both the magnet and the calorimeter come from Soviet Union. And this was the largest collaboration in 70 years history of Soviet Union. So there's Mr. Kai and academician Yifan Wang doing their 3 construction. We published 300 papers and 300 people received their degrees. But these 300 papers, one of them is included in the front page of Scientific American, can be summarized in a few words. First, there are only 3 kinds of electrons: electron, muon, and tau. There are 6 kinds of quarks: UDS, CBT. This is within the available energy. And electrons and quarks have no size. The radius now is less than 10 to the minus 17 centimeters. Unfortunately, the results are in excellent agreement with the electroweak theory. When the experiment agrees with the theory, what you learn is limited. It's only when the experiment confronted with the theory, you learn something new. So for me, I invested 21 years in this experiment, and it's not a big success. After the ultimate untimely shutdown of superconducting supercollider SSC by the United States Congress, I spent quite some time thinking of my future research. I realized I've spent much of my career in different accelerators. So maybe I should do something new, something I know nothing about, something most people consider impossible. And this is how I propose the AMS. The first cartoon I get from my collaborators is time we face reality. We are not exactly rocket scientists. When we started, we have a very large group. Not a single person have ever done anything in space. No one has any experience. This shows experience is not that important. So let me share with you the current experiment on the space station. Cosmic rays are absorbed by 100 kilometers of Earth's atmosphere, which is equivalent to 10 meters of water. So the property, the charge, energy of cosmic rays cannot be studied on the ground. They are very important experiments, study energy and study distribution. But what is the original property? With the exception of photon, charged particle, you cannot distinguish different nuclei. Measurement of charge, origin, energy of cosmic ray require a magnetic spectrometer in space. So AMS provides precision, long-duration measurement of cosmic rays to study the origin of cosmic rays, physics of dark matter, antimatter, and space radiation. So the Institute of High Energy Physics in Beijing is a founding member of AMS experiment. This photo, which shows H.S. Chen and Yifan Wang and others, this is the first meeting at Johnson Space Center in 1994. This is a space version of precision detector normally used in accelerators. And so you have a transition radiation detector, identify electron positron, 9-layer silicon track, measure absolute value and sign of the charge and momentum. A ring image Jerome curve counter, measure charge and energy. Electromagnetic calorimeter, measure the energy of E plus E minus. Two-time applied counter, measure charge and energy, and the magnet identified sign of the charge and momentum. At first, we built a superconducting magnet. Then after the magnet is finished, we found the magnet fit to design value with superfluid helium of 1.8 K and duration 3 years. Just before, 2 months before we installed in the space station, NASA announced they will cancel all the space shuttle. That means after 3 years, we will have nothing. And so I remember this on April 16th, 2010, in the afternoon, I decided to change the magnet to a permanent magnet. So this magnet is still there, waiting to be used. The transition radiation detector identifies electron positrons and use 5,000 proportional tubes, 2 meters in length, centered to 100 microns. And filled with xenon and CO2, it will last to 2040. Silicon detector mostly developed in Italy and Switzerland. We have 9 planes which measure the momentum and charge. Electronics. Since we use particle physics detector, so the electronics is much faster than what NASA provides. And also to avoid confrontation with export rules, we decided to buy the commercial electronics and test them in the electronics laboratory to make sure they're fast enough and reliable enough. So IMS on the space station produced 7 gigabits per second. And the signal is processed by 650 processors. These microprocessors are all specific design, and they have 2 to 4 redundancy, total 228,000 channels, and this process the signal to 10 megabits per second to white sand and to our control room itself. So the detector was quite expensive, but it was mostly done in Europe and China with strong NASA support. So in the United States, mostly MIT, and then there's Finland, Netherlands, France, Portugal, Spain, Italy, Turkey, Switzerland, Germany, Korea, China, including Taiwan. Let me make a comment. In space, because of the rotation of the sun and rotation of the Earth, the temperature changes quickly. So thermal control is one of the most vital things in space. And there's a university in Shandong province under Professor Chen Lin made the most important contribution to the thermal system, together with Professor Wei Wei-Xu, Sun Qie, and Zhui Qi, and others. This group, like MIT group, had 0 experience in space. But what I have decided to choose collaborators, not depend on their experience, but depend on whether they're interested in the project or not. So the detector has 5 kinds: TRD, time of flight, silicon tracker, re-emission and calorimeter. So different particles go through different traces. And so we are measuring all the elementary particles and all the elements across the periodic table. This is the first time you can measure all of them. So we measure the momentum, measure the charge, measure the rigidity. Rigidity is a new term, momentum per unit charge. Measure the energy, measure the flux. So we have been in space now for 14 years. The question is, you have no shutdown. You have nowhere to check it. So how do you know your detector is still working? And so we have many redundant systems. So for example, the inner planes, layer 2 to layer A, will have many lasers to check the relative motion. The outer planes, 1 and 9, they check with cosmic rays every 2 minutes. And so in 14 years, we see the accuracy 2 micron for plane 1 and plane 9. So it's stable to 2 micron in 14 years. In space, one of the most serious things, you do not know what's going on. At least for me, I spend enormous amount of time to see what could go wrong, or when we have to stop to check things. once you know what's going wrong, you can correct it. Well, but if something goes wrong, you do not know, you're going to make a mistake. So there are many physicists, Professor Chile Wen, Professor Wei Wei Xu, Hang Qiang from Taiwan, and Professor Zhu Haoli, and Dr. Yi Jia, who used to be, most of these people used to be at MIT, and now many of them have to return to China. Cosmic ray was discovered in 1912. Cosmic ray experiment in the last 100 years typically has 50% error. Those are the data. And these are the theoretical models. So the model always agrees with the data. When you have a data 50% error, it's easier to confirm the theory. So this was before AMS. In the last 14 years, we have provided data to 1% accuracy and to multi-trillion electron volts. And so the yellow point is the AMS data for different elements. And they are in disagreement with theoretical models. There's no model who can confirm our data. You can adjust a parameter to agree with one, but the same parameter cannot agree with any of the others. And so the AMS data require the development of a new comprehensive cosmic ray model. For galactic cosmic ray, there are two parts. Primary, they are produced in stars and accelerated by supernova. And the secondary, they are produced by collision of primary with interstellar media. So measurement of cosmic ray nuclei flux are important in understanding of the origin, acceleration, propagation in the galaxy. The first surprise on the galactic cosmic ray is primary cosmic ray has two distinct class and totally independent from secondary. So primary cosmic ray, like helium, carbon, oxygen, their absolute value is different, but their rigidity dependence is exactly the same. Similarly for secondary cosmic ray. That means cosmic ray, actually it's very simple. They, even though it looks complicated, but they only have two classes. If you look more carefully, the primary class actually have a subclass. And so there's the light element, there's the heavy element. And secondary cosmic ray also have two subclasses. These are not predicted by any theoretical model, to my knowledge. So today, we have measured 250 billion events to provide precise spectroscopy of cosmic nuclei. So we measure hydrogen, helium, and the separation is 1 part in 10 to the 9. And between ion and cobalt, separation is 1 in 100 because of the low rate of cobalt. All these cosmic rays can be separated into basic two classes. Two primary classes for the primary element and two secondary classes. It's really amazing how simple it is. We do them precisely. And this goes from 30 GeV to 3,000 GeV. So I want to mention, we have many good physicists. Dr. Q Yang used to be MIT, now I have is one of them. we now measure the precision measurement of isotopes. Isotopes of particles with same charge, different mass. So we have a very precise velocity measurement device called RICH, and the velocity resolution is Z equal to 4. It's 4 parts in 10,000 at the speed of light. So this is a very precise measurement of velocity. With this, you can distinguish mass. The first surprise is the origin of cosmic ray deuterons. Helium, carbon, oxygen interact with interstellar media, produce deuterons and helium-3. That was what everybody think before the OR experiment. Therefore, deuteron and helium-3 are both known to be secondary. But we found the flux of helium-3 increased to energy to 4 GeV and then progressively decreases. If deuteron is pure secondary, then the ratio of deuteron to proton must also decrease with energy, but they become a constant. So the velocity, so the dependence of proton over deuteron, proton over helium-3 are totally different. That means there must be something else besides secondary. It's no primary. But no one knows why it is this. We also measure lithium isotope. There are a lot of interest on lithium-7 as a primary component. And this is one of the models of lithium-7. And this is different from our measurement. We have not found any model can fit our data. And then there's a result on beryllium isotope. Beryllium has 3 isotopes, 7, 9, and 10. Stable beryllium-9 propagates through the entire galactic halo, and beryllium-10 decays to boron-10, and therefore the ratio tells you the length of the galaxy. This is our measurement, fits one of the model, shows the length of the galaxy is 3.7 plus minus 0.5 kiloparsec. This looks a good fit, but unfortunately, the same model does not explain other data. It's good for this data, but it's really not valid. And then let me share with you results on cosmic elementary particles, positron, electron, antiprotons. They can have only three sources. One is cosmic radiation, interact with interstellar media, produce positron, antiproton. Another is dark matter collision, produce positron, antiproton. Another, some pulsar, a rotating neutron star, produce positrons, but it does not produce antiproton. This is our measurement of positron spectrum. There are 4.5 million events from very low energy to 1,000 GeV. Cosmic collision is what you expected. Can't explain this low energy part. The question is, what is this? Why there's such a large access? And also, it goes down. The most simplest explanation is this must come from either from pulsar, from dark matter collision, because these are the only two sources we know. But more important is the spectrum suddenly goes down. And so you have a cutoff at a very high confidence level. Nobody predicted that. So we'll continue the experiment to 2030, and so that the data in this shape will become data in this shape. This is the same graph, except from 0 to 200 GeV, it's a log scale, 200 to 2000 linear scale. And so you can see the data agrees with the positron from dark matter collision, but you certainly cannot claim that. You need more data to make sure you have a better agreement, and you also should see the point without dark matter contribution, because the finite mass dark matter cannot produce very high energy positrons. So that is exactly what we're doing. Another unexpected thing is cosmic antiprotons and positrons. We found the measured positron antiproton spectrum and positron spectrum above 60 GeV is exactly the same, the research factor 2. So the identical behavior of positron antiproton above 60 GeV exclude pulsar origin positron, because pulsar does not produce antiprotons. Then there's a very important subject, and that is heavy antimatter. Matter is defined by its mass and charge. Antimatter has same mass but opposite charge. So the question is, where is antimatter star made of antineutron, antihelium, anticarbon, antioxidant? For this, you need a very precise detector to look for it in space. These are two antihelium candidates. So this is a bending plan, non-bending plan in Cherenkov ring. This event have a charge -2 plus minus 0.05, mass 3.81 plus minus 0.3. And this one charge -2 plus minus 0.05, mass 3.15 plus minus 5.3. Just the opposite of helium-4. These events cannot be produced from cosmic collisions because these are rather high rate. So after 14 years, we have enormous amount of matter, electrons, protons, and nuclei. We have quite a bit antimatter, antiproton, antiproton, and positron. This can be explained from dark matter collision, from pulsar, or from cosmic collision. But the candidate of antihelium cannot be explained by this. And these are very clean events, no backgrounds whatsoever. We are now looking for anticarbon and the antioxidant to ensure you indeed see an antimatter universe. Now let me touch upon a very important subject with the current NASA administration, that is long-term interplanetary exploration. Lethal cosmic radiation is approximately 300 rand. To survive a long-term mission for Moon and Mars require complete radiation knowledge being uniquely provided by IMS. So lethal cosmic radiation now is being measured accurately with weight, time dependence, energy dependence, elements of periodic table. So IMS results are mitigating the lethal effect cosmic radiation for safe exploration of Moon and Mars. Cosmic radiation from galactic cosmic ray, and the first around the Earth, the radiation in low Earth orbit from interaction with the atmosphere and trapped in Earth's magnetic field. Radiation in the interplanetary space on mission to Moon and Mars will lose the protection of Earth's magnetic field. In addition, there's radiation from the sun called SCP. First thing we found, radiation is not a constant. This is an example of proton was similar for all the elements. Hourly, from 0 to 6 to 12 to 18, every hour the radiation is different. And daily, every day, December 1st, 7, 15, 22, every day is different. And every year is different. And this is very, very important if you want to leave the vehicle, go out, you may want to choose this area, not this area. So cosmic radiation varies hourly, daily, yearly, and cannot be predicted by current model. And this is from SDIT of Chengling and Weibei. That is energy dependence of the electron flux over 22-year solar cycle. And this is high energy gradually decreases with energy. You see the structure gradually disappear with high energy. And the dangerous region, it varies year by year, day by day, hour by hour. Even for the simplest thing, elementary particle, in interplanetary space over the 11-year solar cycle, you can look at the particle with same mass, opposite charge, proton, antiproton. Their functional dependence and function of time is quite different. For the electron, positron, they are similar. For the particle with same charge, different mass, electron, antiproton, they are very different. The absolute value, of course, is different. It's the functional behavior. It's also quite different. But this, only the absolute value is different. The functional behavior is the same. And then there's positron, antiproton, for particle, antiparticle. But this is quite different, but this is the same. So this is a unique information for understanding cosmic radiation as function of mass, charge, and energy. This has nothing to do with the current cosmic ray model. Then there's a relationship between positron, electron, and proton. And this also comes from Shandong University. So what is the relationship, the daily rate at 1 GeV between electron flux and proton flux? In 2011, it's this red point. In 2016, it's in this relation. 2012, 13, 14, and then 15, 16, 17, 18, 19, 20, 21, 22. So it's a hysteresis. But for proton and positron, it's a linear relationship. Something totally unexpected. Then another curious thing is helium. Helium in low Earth orbit. In the energy range between 100 to 4,000 GeV over a large area of plus minus 35 degrees, only helium-3 exists. Helium-4 and helium-3 are in the outer region. So this is a very important curve. That is a summary of skin dose from different nuclei over the 11-year period. And so since the radiation damage proportional to this square, so proton and ion have the same radiation dose. The lethal dose is about 300 grams. This is over the 11-year period. This is the plot of sunspot for solar cycle 24, solar cycle 25. And so for solar cycle 24 in 2014, the polarity changes from negative to positive in solar maximum, in solar minimum, go back to solar maximum. And this part is remain to be measured. So at solar minimum, 3-year dose is 240 rand. The lethal dose is 300 rand. But this 300 rand is an estimate from Hiroshima and Nagasaki. And so this is very close to lethal dose. More important, which year you start really depends on accurate measurement of this. This is the first time made available. We are now upgraded detector, and the leadership of J.C. Wang from IHAB. So in a few months' time, we're putting another layer, come up with SpaceX, and then use a Canadian arm to take this out and use 4 astronauts to connect 74,000 channels to the electronics. Much of the detector were done at the IHAB and at the STIIT under the leadership of J.C. Wang. And there was J.C. Wang here. And they really did a very good job building this spectrometer. When we first went to space, Scientific American had an article about space station Zhongguancun, about AMS. The discovery of the J particle 50 years ago opened a new realm of physics. Space is the ultimate laboratory. Space provides particles with highest energies. AMS result required the development of a new model of cosmos. So thank you.
Okay, thank you very much for the beautiful lecture on modern experimental physics. So let's open the floor for questions.
I'm surprised no questions.
Yeah.
Thank you for a beautiful lecture. It's very stimulating to see that there are so many experimental results which are not explained by theory. Could you maybe give us a hint or a guess where you think which ones of these most likely will have a chance of being explained first? Which ones of the experimental results that you have discovered that we know about that has the most likely chance of being explained by theory in the future?
I'm absolutely incompetent to do that.
Thank you.
Any questions? Yeah. 你们准备多点麦。
A student from Southeastern University. I remember you said to us that your experience is that you doubt yourself forever. Yes. So my question is, what kind of belief deeply in your heart that made yourself personally contribute to experiment physics for nearly 70 years? Yes. Thank you.
I did not understand the question.
Could you repeat again?
Yes, I should say it slowly. Yes.
No,
Yeah. Okay.
I did not understand.
Yeah. My question is, what kind of belief deeply in your heart that made yourself personally contribute to physics for nearly 70 years?
Why are you so enthusiastic about physics?
What do you want to?
What makes you to be so enthusiastic? He asked you, why do you have so much enthusiasm? And what drives you to work so hard?
I guess I'm somewhat curious.
Other questions? Yeah.
Thank you, Professor. I have two quick questions. The first one is, how do you distinguish between cosmic background deuterium and this accelerated deuterium? The second quick question
No,
is...
one.
Okay.
Cosmic produced deuterium compound space.
Yes.
You can trace it because its detector is so accurate. You can trace the far 50 or so radius away. Accelerator, you are within 100 meters from the accelerator. So no question to distinguish them.
Okay. The second quick question is, can AMS look at different directions in the sky? I'm asking because if we want to know whether it's the origin of that positron is from dark matter, we may look at towards galactic center or look against galactic center. And if we see a difference between the two, probably that will be a more...
Yes. There's, we have a large angle, but you cannot look the direction because you do not know the intergalactic magnetic field. A charged particle bends in a magnetic field.
Okay.
Therefore, you will not know.
I see. Thank you very much.
Other questions? Okay, if not, thank you very much indeed. Beautiful lecture. So we come back at 11. We have some gift from our students from Children College to the speaker. So just wait 1 second. Yeah. Okay, now. Go up. So here's a Sam, pull the thing. Pull the thing. There's a gift from students for you. From the college in Tsinghua University. It's a gift for you. Yeah. Okay, thank you.
Moment ago. Yeah, take a seat. He will come back. I will. 他不是他走就什么。He was sitting next to me.
So you get your degree?
Yes.
So how long it took you?
It's about right. It's about right because otherwise you wouldn't get questions. David Gross couldn't allow him to get questions because he a little bit exceeding the time.
Thank you.
Yeah, he probably went to the restroom.
Who's next?
Steve Chu. So you have choice whether you can leave now or you take some rest. It's up to you. And then afternoon, I just figure out it's at 7 p.m. So you had some rest and then you come to the panel discussion at 7.
Before 7.
Before 7, you can have your rest.
No. What's going on here?
Here we have talks by Steve and by Honori. There were 2 talks, and then there is a buffet dinner, and after buffet dinner is a panel discussion.
What is panel discussion?
The panel discussion is just a few people sitting there taking questions. So it is going to be moderated by Henry Tai. Do you know him, Henry Tai? He was the professor at Cornell. He's one of the founding member for the inflation, astrophysics theories. I've been working with Alan Hughes. Yeah, you can.
So we need to find out.
这样，你那个下午的晚上的那个几张都明天你们都没有。
Okay, let's sit down. The next lecture will start immediately. Please sit down. Oh. Sit down, Steve. Okay, our next speaker would be Professor Steve Zhu, who used to work in high energy physics and then moved gradually to important topics that has spectacular applications which influence modern science, modern technology. So we would have Steve. Where's the speaker? Oh, that's right.
Okay. Right. Thank you for those of you who want to depart from the most fundamental questions in physics, as exemplified by the two earlier spectacular talks. I'm going to go down to something pretty mundane, but really I also want to touch base with this audience and talk about things that possibly you can understand. So the main theme of this is that science doesn't always advance with a clear vision and a well-executed plan. As we just heard, the most exciting things in science are when you get surprises. And indeed, some things just happen by accident. So to give you an example, I show you my father and my mother and my father's oldest sister on their wedding night. Very distinguished family. My father's oldest sister was a full professor at Tsinghua University in chemistry before World War II. And she's been often recognized as perhaps the most significant women chemists in pre-war China. But after the Communist Revolution, she had to come to the United States, and being a woman, being Chinese, she couldn't get a job that equaled the distinction of Tsinghua University, so she could only get a job teaching at a small college meant to teach young ladies how to teach elementary and high school. Nevertheless, she was still a spectacular organic chemist, applied for an NIH grant in a place that didn't have any research, and for the next 25 years, she was funded by the National Institutes of Health, which paid in those days for this small college to establish a laboratory. So that was my aunt. My grandfather, Xu Tinli, went to Cornell as a graduate student in civil engineering. He came back and in just less than a decade became the president of his university at the age of 30 years old. After the revolution, he too had to leave, penniless, nothing, no job, no prospects of being a professor. So he had to reteach himself civil engineering, which he did, went into his business by himself. And by the time he was born in 1900, by the time he died in about 1990, just before, he received the highest award for the American Concrete Institute. So he had to start all over again, but still managed to survive. And then his older brother was a professor of physics at Peking University, also Academia Sinica. His thesis advisor was Perrin. Perrin got a Nobel Prize for his work on Brownian motion, which turns out intimately connected with my work. And as the French tradition, when someone gets a Nobel Prize and there's a graduate student who did the work, they actually give him a medal. So he got this medal. So very, very distinguished family. How could they produce something like this? This is me. I want you to feel even more sorry for myself, for me rather. I come from not only a distinguished extended family, but I had two brothers. My oldest brother went to high school, set a record in the history of the high school for the highest cumulative average. He goes to Princeton, gets a PhD in theoretical physics in MIT, and then after he realized it's very hard in the 70s to get a professorship in theoretical physics, high energy physics. So he went back to medical school, got an MD, PhD. And he's now a professor at Stanford in biochemistry and oncology. My younger brother is the smartest of the three of us by far. He has 5 degrees, a PhD at 22. Even though he didn't graduate from high school, he just skipped his senior year. He was rebellious. But he talked his way into UCLA after a year. And he's the most famous and certainly the most expensive patent litigator in the United States. He's president of the board of overseers of Harvard, so on and so forth. So I was the first male child in my extended family not to go to Harvard or Princeton. So you should really feel sorry for me. But I went to the University of Rochester, which was actually a blessing. No one heard of my family, and I thrived there. I went to the University of California, Berkeley. At the time, had 9 active Nobel laureates in physics and chemistry, and that's where I spent my early years. And while I was at Berkeley, I began to notice it was, at that time, the greatest physics department in the world, and I learned that new instruments allow you to see new things with new eyes. And so I told myself, you know, if you're the 100th person to look under a rock, you're not going to find anything new unless you're exceptionally intelligent. But if you're the first person to overturn the rock with a new instrument, you don't even have to be smart to discover something. So my vision was, given my insecurity complex, not being smart, I will help build new instruments and maybe I can get lucky. There's if you step back and look at this, we always think of science as giving technology, but as you witnessed, especially in the last 2 talks, this actually goes the opposite way, that technology quite often leads to very new physics, and it's the pursuit of technological goals that have led to some of the most innovative science, and as I said before, new instruments allow you to discover new things. So when I was at Berkeley, as mentioned, I started life with Eugene Cummins. He was an expert in beta decay. And then while I was a student there, I was messing around with some failed experiments. And then quite suddenly, the Bouchiats published a paper that said, in a laboratory experiment, you can actually test the Weinberg-Slalom glass shell model. It required a very, very good laser, one you could not buy. And so that's me constructing this laser. It took me 5.5 years, 3 years, and plus 2.5 years more. 2 years as a postdoc and 3.5 years as a graduate student. It was pretty lackluster, but for whatever reason, I don't to this day fully understand, but they asked me the physics department at Berkeley asked me to apply. So I applied with a 3-sentence letter. Dear Professor, the chair of the department was Jeff Chu, a bootstrap theorist, and said, Dear Professor Chu, my advisor says I should apply to Berkeley. Can you consider this letter my application? And they hired me. But I hadn't published a single paper, so it was a little bit crazy. My graduate students and postdocs today assure me that could never happen today. But in any case, I worked with a beginning graduate student who was going to be my first graduate student. I get a startup package from Berkeley. I use it to buy lasers and off and running. So, but they said, since you spend all this time at Berkeley, we'll give you the opportunity to go somewhere else for a year or two, and then you can come back, but here's your startup money. You can start your group or you can go away. And I said, I'll take the money, I'll start my group, and I'll also go away. So where did I go? I went to Bell Labs. It was a spectacular place. 15 scientists, between 15 and 14 scientists got there, did work there that received Nobel Prizes. And so that was part of what was happening. And I'm not going to go through this, it's too long, but I had a lackluster couple of years at Bell Labs. But finally, I went to Bell Labs Homedale. I was asked to start a new basic research department in the sister lab at Homedale. This is what it looks like. And the water tower looks amazingly like a transistor. But in any case, while at Homedale, I started the work on the laser cooling and trapping of atoms. Now, how did I do this? Well, I was a department head, and a fellow department head was a fellow by the name of Art Eshkin, a truly brilliant pioneer physicist. And he had this dream of trapping atoms, but it started with trapping particles. For example, if you took a laser beam and put a little polystyrene sphere in a tank of water, if the particle went to the left, there would be higher intensity here, so it would be pushed over here. If the particle went to the right, it would be pushed over here. And so, yes, you can see the cursor. So in any case, that was great. He called this a dipole force, and you can analyze it in several ways. But one of the ways he analyzed it is if it was a macroscopic, several micron sized particle, you can actually think of it as a lens, and the asymmetry in the bending of the light rays, because the light was not uniform, would actually force the particle to go to the center. I prefer to think of it in a different way. And again, stepping back and saying, what was he really interested in? He was interested in holding on to neutral particles, but not by getting atomically close and touching it. So the atoms in your finger, the atoms in the marble would actually get within angstroms of each other. He thought the following, that if you think about static electricity, you have a charged rod. It induces a dipole moment, a little separation of the positive and negative charges on this neutral particle, like a dielectric sphere or something. So this induced dipole moment, P, the energy goes as a minus P dot E. And so if you look at that, you find that this particle wants to go to a region of highest laser intensity. So the force is the gradient of the energy. All right. Now, it turns out, that if you, there's a theorem that says, can you arrange charges around some boundary so that you create an electric field maximum in a region where there is no material? And there's a theorem called Earnshaw's theorem that's impossible to make a static electric field. Now, when I heard about this, I said, well, I don't understand. Why is it called Earnshaw's theorem? Why isn't it just Maxwell's equations? And in Maxwell's equations, that's one of Maxwell's, the integral form of Maxwell's equations. And if the divergence of E in a region where there's no charge is equal to 0, that means if my intuition about divergence is if you have a sphere, the definition of divergence, you have a spherical surface, you look at all the flux lines going in, all the flux lines coming out, and you shrink the boundary to 0. So that's the real definition of divergence. And so flux lines going in and out are equal in number. So if the force is proportional to these flux lines, you couldn't actually trap a particle. Okay, so that's a much better way of looking at it, I thought. But you can violate Earnshaw's theorem because it's a theorem in static electricity. So if you focus the laser beam, you have an oscillating electric field that creates an electric field maximum. Okay, however, it was shown by Jim Gordon. Jim Gordon was a brilliant physicist at Homedale. He was the graduate student who worked with Charlie Townsend, the first maser, and he found that this mysterious dipole force, if you tune below or above resonance, it would switch signs. As I was beginning to get interested and asking Art and also John Bjorkum what's going on with that, and he said, oh, that's very complicated. Only Jim Gordon knows. But that's not true because I was putzing along, and the way I work is if I can't reduce the freshman sophomore physics, I feel a little bit stalled and refuse to go further. So everything I was doing was being reduced to freshman and sophomore physics. So consider a harmonic oscillator. The harmonic oscillator is the charge on an atom, and there's an absorption, and there's a phase response. And because of that, in phase, below resonance, you're in phase. Above resonance, you're out of phase. So if you're below resonance and you're in phase, think of that electric field as oscillating, but the charge on the particle, the induced charges on the particle are in step with that field. So it reduces to static electricity. And that's all it was. But if you go above resonance, then you know the response of harmonic oscillators, you're 180 degrees out of phase, so it flips sign. So all this was just freshman physics. And so that was good, took the mystery out. Okay, so then at the time, ions were being trapped, and after they were trapped, people were cooling them, Dave Wineland and his colleagues at National Bureau of Standards. And so the idea was trap an atom and maybe you can use light to cool it. And so the idea is very simple. Suppose there's an atom and it's moving to the right, and you shine a laser beam on it, and you shine another laser beam on it, and you play one simple trick. You tune the light so that it's below the natural resonance of this atom. And what happens is this atom is going towards this laser beam, and a Doppler shifts it into resonance. It's going away from this laser beam, so a Doppler shifts it out of resonance. Now consider the scattering of many, many photons, time average, and what you find is there's a force opposite its motion. And of course, if the atom goes to the left instead of the right, the Doppler shift just reverses, and it looks like magic, it cools. So I got very excited by this. I wasn't really reading the literature. It's a fault I still have. And so I started doing this experiment, and within a year from the idea, I went to my director, Art Ashkin, and said, not Art Ashkin, I was the fellow department head, my director was Chuck Shank, and I said, this is really simple, it's gonna work. He looked at me, he had closed down the laser cooling effort of Art and his colleagues, but he said, okay, you can do this, but don't try to talk anyone else into wasting their time. You got Positronium to work, you can waste your time. And so now, why didn't other people, for example, Hensch and Shallow, or others in the 10-year interval do this experiment? And they forgot one simple calculation. If you put this atom in this sea of counterpropagating laser beams, it creates a drag force. It's easy to show this. And if there's a drag force, but it's being buffeted on all sides by photons, there's a stochastic noise. So its analogy was like a Brownian particle. You got a little sphere, and it's being buffeted on all sides by Brownian motion, but it's got viscous drag. So I started to write a program and remembered my sophomore physics and said, I don't need to write a program. Einstein figured this all out. And lo and behold, if you put atoms in this soup, it would hang around for a second. So all of a sudden, that's what got me excited. And I said, this is so easy, it's really gonna work. Okay, now we got lasers cooled, optical molasses. The temperatures were very cold. They were about 1/4 of a thousandth of a degree above absolute zero, but I made a really bad mistake because it looked like it was actually less than 0.1 millikelvin. But I was so guided by theory, I convinced myself of some argument that said, well, you know, I've had big error bars. Anyway, lesson to the young people, don't be guided by theory. And anyway, but we had these cold atoms, 1 million of them in about a cubic centimeter. And yet it didn't look like we could trap them. We tried a few ideas. And of course, Ashkin had already suggested the simplest laser beam if you can focus it in a very tight, small spot. But the trapping volume was about 10 to the minus 6 centimeters. So you get one atom. And one atom trapped out of 1 million atoms that are diffusing around is not going to make a great signal. And so what was going on? And so this simple focused laser beam trap was considered way impractical. And it took me a couple of weeks to realize, wait a minute, you can use random walk again. You've got an atom in a trap, and if it falls in, you oscillate between cooling and trapping, and it falls into the little potential. It's great, you got one atom. But there's Brownian motion around, and it's very rapid. And so there's all these other atoms that go to the boundary of the trap and also fall in. So you can easily convince yourself over a good fraction, a half a second, you can get thousands of atoms landing in the trap. And that's all it took. It took another random walk diffusion realization. So it worked. And that's me when I was younger, before the phase transition. Never mind, that's my phase transition. And Art Ashkin is staring at this apparatus. So the idea that you can have a single focus laser beam trapped in optical molasses, the molasses was like a fluid. And then the optical trap was this little potential well that atoms would fall into. And then during this time, Ashkin said, you know, this optical molasses, we can do a macroscopic experiment. Instead of optical molasses, you just use water. Instead of an atom, you use a bead, and you have a single focus laser beam. But you notice in 1970, he was very close to this. He had just 2 focused laser beams. And so why did it take 15 years to realize that if you put the little particle of water, the water would be the molasses that would keep the particles cold, and it would have worked. Now, there's a huge difference between 2 focuses moving around like that and a single focus and moving a mirror. So when you have a single focus laser beam, you also had what we called an optical tweezer trap. And in the same year, we published the cooling of, a trapping rather, of atoms. Art Ashkin published a lensing system that he had an objective with high numerical aperture. This happened to be a water immersion objective, and he could actually trap particles. So this was very exciting. So one day he comes into my lab, and he's wide-eyed, and he said, Steve, you can't believe this. You got to come to my lab. I said, what? What happened? He says, I've discovered life. Okay, what do you mean? So I look in this apparatus with a Edmund Scientific really crappy telescope, and you see this little thing going around, and then he turns off the light and it swims away. It's New Jersey water. There are bacteria in New Jersey water. And so it found out he could trap E. coli, and if he used infrared light, he can trap them, move them around at will. And in fact, he later showed you can have, for example, a yeast crawling along. Using the optical trap, you can reach inside, grab organelles, that's little thingies in the cell, it's a technical term biologists use, and you can actually pull this organelle down with the trap, let go, and it kind of springs back. It's kind of like an optical trap. We can reach in, grab your liver, pull it a little ways, let go of it, springs back. Anyway, this set off a great series of experiments by Art Ashkin, who later got a Nobel Prize, much later, for his work in biology, and which really led to the optical manipulation of molecules. The first optical manipulation of molecules was done by me when I got to Stanford, because I was inspired by Art Ashkin. I said, look, we can trap atoms, you can trap bacteria. Can you trap and hold on to individual molecules? And so I thought, well, if you glue a little handles, polystyrene spheres to this. You can do this. This is an example of a movie where you see a long piece of DNA lit by fluorescent dyes on the DNA. You hook this laser beam on a little joystick that tilts the mirror, and you can just play with the molecule. After a day or two, and then my graduate students were playing at night, to them it was a video game. I said, no, maybe we should do some serious science. But anyway, it led to a lot of interesting things. By the way, this is me when I was 40, arriving at Stanford. And one of the first things I did, besides the biology, was I said, you have really cold atoms. You can toss the atoms up, and they're so cold, they just go up ballistically and come back down and in a so-called atomic fountain. And even when I was a graduate student, I knew of a failed experiment at MIT. The graduate student worked on it for many years. He had difficulty getting a PhD. He struggled because there was never any cold atoms that came up and come down, but the fast atoms would knock the cold ones out of the way. But he made out okay. This graduate student's name was Ray Weiss. And, but anyway, he never published this experiment until his Nobel lecture. But I knew about it from word of mouth. But because of this, I said, you know, if you have cold atoms in a high vacuum, you toss them up, there are no fast atoms behind it. So they'll go up, they'll come down, and you can do precision microwave spectroscopy. So the first thing was you trap this. There's another trap called a magneto-optic trap that I don't want to talk about, also demonstrated by Bell Labs. You had a little fountain, goes up, it comes back down, and you do some radio frequency microwave spectroscopy, which was the, very quickly became the microwave hyperfine splitting, first of sodium, but then cesium. And so in a very, very short time, less than a decade, the atomic fountain, atomic clock became the standard of the world. And it's progressed since then, and Junyi at the University of Colorado Boulder and Jilla now has about 21, it's a little bit better than this, it's about 21 or 22 digits worth of precision in the energy level. That's a lot of precision. To give you a sense of it, the age of the universe, this is an old slide, maybe 13.5 billion years old, it's a number of seconds. And so if you started one of these clocks when the universe was born and asked how accurate it would be a couple hundred milliseconds. It's very good. You might ask, what are you doing? You don't need that precision in anything. Aren't you just showing off? And the answer is, of course. We're showing off. But it turns out that measurements of time and frequency shifts are the most accurate measurements in all of physics because we can count really well. And so counting, and now counting optical frequencies has now become a reality, another Nobel Prize. You have this great precision. And so these are some of the examples of what you can do with this great precision. Another thing we did when I was at Stanford is you take an atom and you have two counterparting beams of light that go to a virtual excited state back down to another ground state. So when you go up to the excited state, it absorbs a photon, the atom gets an impulse this way, and then this stimulates the atom back down in a virtual state, so you get another impulse the same way. So by making transitions between ground states, you can actually put photon momentum on the atom. Because it's a coherent process, you can make a coherent superposition of states. And over the years, many, many years, even beyond this, we can add just not 2 photon momentum, we can get 100 photon momentum. Make very, very precise so-called atom interferometers. These atom interferometers, first demonstrated by Mark Hesvich and myself in 1991-92, are now the most accurate way of measuring gravity by far. It's being used to test equivalence principle, and it's being used as the next generation gravity wave detectors to complement LIGO because it's in a different frequency spectrum. Okay, so then I go on, and I was happily minding my own business, and I was asked by my former boss at Bell Labs, Chuck Shank, and also by Bert Richter, who was then director at SLAC, that Chuck is retiring from being a lab director for 15 years. Would I consider taking the job? I said, no, I'm very happy doing research. The last thing I want to be is a bureaucrat, with all due respect to deans and presidents out there. But they asked me again. I said, no, not really interested. But it says in the Bible you have to say no 3 times. And the third time, Chuck said, oh, look, just show up. And if you like what you see, why not give it a shot? And I was thinking, by this time, this is 2004, I've been 4 years talking about climate change and how serious the problem might be. And here's this wonderful laboratory just above the University of California in Berkeley, very distinguished laboratory. About 3 dozen young scientists started their career there that got a Nobel Prize. So it's as distinguished as you can get. And when I was a graduate student, a postdoc, and a beginning professor there, I too was a member of Lawrence Berkeley Lab. So I said, all right, you can really leverage things if I go and give pep talks about how important it is to at least these brilliant scientists, at least think about it. And if you think of something, you never tell anyone what to do, you just have to get them excited about the possibility. And I used to say, this is a really important issue, but to whet your appetite, I'm sure that there will be Nobel Prizes given for solutions. I did not anticipate there were 2 so far: blue light emitting diode, the light efficient diode, and batteries. There will be at least another 2 or 3 for sure, solutions to this. I was concerned this is the global rise in temperature. I'll be talking about this 3 days from now, but it's getting it's rising very much. And just to remind you, the UN limit of 1.5 degrees, we are passing today. So we're beyond that. Where do I think we're gonna go? First, let me also tell you to whet your appetite so you can go to my talk on Wednesday. Most of the damage that we've done to climate is not visible. And the reason it's not visible is because the oceans are absorbing 90% of the heat, and the oceans are very cold. So it's like you have a glass full of ice cubes, and until you melt those ice cubes, it's gonna stay cold. What determines the weather is the surface temperature of the ocean and the surface temperature of the land. But because the bottoms of the ocean are very cold, close to 2 degrees centigrade, it's gonna take 50, maybe 100 years to warm up. So the damage we've already done is not visible. The weather we will get is not visible for 50 or 100 years. So if you think it's hot now, just wait. In any case, so here was my concern. Here we are. This is no policies. This is current policies, but not being enacted. And due to some, shall we say, backtracking by my president, other countries are similarly backtracking, and we are not going to be following current policies around the world. So we're heading to, best guess, 3 degrees, maybe 3.5 degrees above where we are. We're about 1.5 degrees now, but another 2 degrees. Okay. So for that reason, for whatever reason, I don't know, I didn't do politics, but when President-elect Obama in the 3rd week in November, I get a call and said the President-elect would like to meet you for a very important job. And I said, I don't think I want to work for government. I was thinking of stepping down as director. How important is this job? And they said, Secretary of Energy. So I said, okay, I'll fly to Chicago for that. The previous president, Bush II, wanted to know whether I was interested in being science advisor. I was not. Science advisor is an advisor. Being Secretary of Energy, you have budget authority. So I met with President-elect Obama. He's, it's in his warm room. He's from Hawaii. He greets me and says, everybody says you should be the new Secretary of Energy. I say, who are these future former friends of mine? He ignored the joke. And for an hour we talked. And I was so impressed with him that I told my wife afterwards, how did it go? What are you going to, I said, this guy's really impressive. If he asks me, I will say yes. We talked for an hour about where we stood on the issues. He said, I want two things in my term as President of the United States. 1 or 2 terms, whatever. He said, reform healthcare and do something about climate change. And those are the only things I really care about. So I was very excited by that. And so when I became Secretary of Energy, I used to quote a Sheikh Imani, a former Saudi oil minister, and he said, the Stone Age came to an end, but not for lack of stones. And the oil age will end, but not for lack of oil. Now, that's not have anything to do with why he was a former oil minister. He meant we transitioned to better solutions. And so, and what he really meant was if we don't have better, which includes economically better as well as cleaner for the environment, the oil and gas is going to come out of the ground. And I think it's true. If you got trillions of dollars underneath the ground, and you're a country that has that, you are really, there's a lot of political pressure to bring it out of the ground. All right, so now I was also, so part of my job was the cheerleader for the people, the National Lab Scientists, also the employees at the Department of Energy. And I would say the greater danger, I was quoting someone, the greater danger for most of us lies not in setting our aim too high and falling short, but in setting our aim too low and achieving our mark. That was said by Michelangelo. All you young people out there, these are very wise words. Anyway, there was, some good, some bad. You get congressional hearings where they try to skewer you for doing something, making transitions to clean energy if they didn't believe in that. And then occasionally you get these blasphemous news articles. So one appeared in The Onion in February 2013, and it says, hungover energy secretary wakes up next to solar panel. Let me read you the byline. This is Washington. Sources have reported that following a long night carousing in a series of DC watering holes, Energy Secretary Stephen Chu awoke Thursday morning to find himself sleeping next to a giant solar panel he had met the previous evening. According to sources, Chu's encounter with this crystalline silicon solar receptor was his most regrettable dalliance since 2009, when an extended flame with a 90-foot wind turbine nearly ended his marriage. Anyway. So the press liaison at the Department of Energy looked at me, we smiled at each other. This deserves a response. Anyway, there was also some not so funny things. One of the things that happened in late April 2010 was the Deepwater Horizon, an oil exploration rig exploded, caught fire, drifted to ocean. It just drifted away by 45 degrees. It sank, the pipe snapped, and underneath the water, they had a TV camera that on CNN was showing 24/7 oil and gas leaking out of this. And so there was tremendous pressure on the administration to do something about it. And President Obama's simple thing was, after a cabinet meeting a couple of days later, he just goes to me and says, Chu, go down there and help them stop that leak. Because he knew I was an active scientist. And so I said, okay. Figured I'd, ask a couple, 3 or 4 other people, they all said yes. They said, well, great. Or they said, I have to tell my department chair, maybe I can get relieved of duty. I have to tell my spouse, things like that. But we all went there and met. And for the next 2 months, 2.5 months, I was living half-time in Houston. helping them stop the leak. And literally after the first week, the people, BP, was the responsible company, the engineers and all the top brass decided we weren't going to talk to the press. I said to my little group, no one talks about anything. We're here just to stop the leak. And so they began to trust us, and in fact, we did help them stop the leak. I would fly back, and other cabinet members would look at me and say, Steve, you look happy. How could you be happy in this stressful situation? I said, oh, I am happy. I'm helping solve a problem, technical problem. So this is what scientists do. They get happy when they solve technical problems. Anyway, so that's what happened. I returned to Stanford in the spring of 2013. Why did I only stay 4 1/4 years? Well, it was my dear, lovely wife. She said, she looked at me and said, you know, Steve, no one's irreplaceable, not even you. I'm going back to California. I hope you join me. So I had to explain to the president, I'm sorry, I really would like to stay another 2, maybe even the full 8 years, but I think, you know, I got another boss. And, you know, so I said, okay. We talked. And so I go back to Stanford this spring. You know, I was both, remember, I was a joint appointee at University of California, Berkeley, and at Stanford. There was a difference. Berkeley kept my office, kept my lab space. They loaned it out, but they said, when you come back, we'll give it back to you. And whatever, and all your setup money you didn't spend. And Stanford said, after I went to DC, they took away my lab space, they took away all my discretionary money, and that was it. And that's why Stanford's richer than Berkeley. But my wife gave me no choice. She said, we're going back to Stanford. She was the dean of admissions at Stanford, had all her friends at Stanford, and said, no choice, we're going. So I had to explain to the president of the university and the provost, you know, oh, it was very cute because 2 former secretaries, George Shultz, Secretary of State and Secretary of Commerce, and Bill Perry, Secretary of Defense, they called me up, they heard I was leaving and said, would you mind if we talk to the president of Stanford to say how important it is that Stanford get you back? I said, no problem. And they did. And so, but I told the president and the provost, your life is going to be very simple. There will be no counter bid. My wife has forbidden me to consider Berkeley. And I told this to the general counsel of the Department of Energy, and he looked at me dumbfounded and said, hasn't anyone told you how to negotiate anything? But I said, you know, if I get a new idea, will you help? He said, sure, we'll help. Okay, anyway. So there were some new ideas. I want to go briefly on this little cartoon of how people try to anthropomorphize biology at the molecular scale. So this is this cartoon of Kinesin walking, but it doesn't work like that. Erwin Schrödinger, in a series of lectures he gave in Ireland, Trinity College in Dublin in 1943, later put into a book called What is Life, which I read as an undergraduate and reread again and again. And he said something very profound. He said, from all that we've learned, in that book, he's predicted there's got to be some storage of information because that's the key to biology. Maybe it's stored on a linear polymer, i.e. DNA, you know, kind of a pure thought. That's how brilliant he was. But he also said, from all that we've learned about the structure of living matter, we must be prepared to find it working in a manner that cannot be reduced to the ordinary laws of physics, not because there's any new force, but because the construction is different from anything we've yet physically tested. So what is he talking about? So I translated this and said, look, man-made machines work where friction is minimized. We use ball bearings, we use lubricants, and they have inertia, and they spin. But in the molecular world, it's entirely different. It's embedded in viscous fluid. There are thermal fluctuations that dominate. So if Newton were the size of a bacteria but had the brain of Newton, his laws of motion would be very different. An object in motion would quickly come to rest. That means F is not proportional to acceleration. F is proportional to a drag force and velocity. And there's Brownian motion. And just how living organisms can survive and operate in this very dissipative, jiggly world is the subject of my July 15th talk. I will skip some of this and just go on to ending. So there's some time for questions. We're going to go over 550 parts per million CO2. We emit, including methane and nitrous oxide, the equivalent, and other things, we emit the equivalent of maybe 50 billion tons of CO2. Because we can't get the greenhouse gas emissions out of agriculture for at least a couple of decades, we don't have the technology to replace fertilizer. Just the using of fertilizer, not the energy of fertilizer. Putting fertilizer in the ground, not absorbed by plants, results in N2O emissions, which is 300 times worse greenhouse gas in the last 100 years. So you got to get rid of fertilizer, but we don't know how. And so, so we're going to need carbon capture, and at least the scale 10 or 20 billion tons a year. And by comparison, all of the landfill in the Earth is only 2 billion tons. But you put CO2 under the ground, it's a much lower density. So we're talking factor 30 or 40 more stuff going into the ground than all of landfill. In fact, not surprisingly, it's comparable to all the stuff we take out of the ground in fossil fuel. It's got to be. It's actually a little more because carbon dioxide is a little more massive. When I was Secretary of Energy, I funded a carbon capture pilot plant. It cost $1 billion. This is the footprint is 1 acre. This is the size of a very large American-style pickup truck, and it required about 30% of the power output from a fraction of a coal plant, 1/4 of a coal plant, $1 billion. This is not meant for wide-scale deployment. It's not going to be deployed, that technology of using amines. And so I'm going to briefly mention that we may have stumbled on a new way of capturing CO2. This is Sang-Chul Kim, a postdoc who's now just taking a faculty position at NUS in Singapore. And what happens is when you expose carbon dioxide to water, very high pH, high alkaline water, the solubility of the carbon dioxide asymptotes to about 0.5 mole per liter, which is a lot. Gas at STP, standard temperature and pressure, is 22 liters. So it was well known to do that, and the only commercial carbon capture actually is using high alkaline water, but once they get it in the water, they have to heat it up. And it's the heating up that makes it very energy intensive and very energy costly. So we thought we could use electrochemistry, and we got very excited that we could shift the pH in electrochemistry with far less energy than we thought possible. It's certainly been demonstrated. This is what the thing looks like. But I'm here to tell you that, and we submitted the paper to Nature. It got accepted with some reviews, but before I told my group, I said, look, there's some problems with the paper, so let's investigate it. Let's not wait for the referees to find it. And what we found was our interpretation was completely wrong. The referees didn't find it. So we're going to have a very interesting reply to the editor because it's completely wrong, but we learned how to fix it. Maybe, okay? So, so I've never been in a position to try to talk my way out of a Nature publication, but, and then in the same breath, talk my way back into it. The model we had was this molecule. It's a reduction oxidation molecule, very inexpensive, one of the cheapest organic molecules you can buy, called TEMPO, TMPO, which is considered for redox reduction batteries. This is our cartoon of a water being polarized by this charge here. And if you consider a reaction that takes a proton, combines with bicarbonate, makes carbonic acid, and finally CO2, that when you use up protons, we thought that this would readily donate a proton. That turns out to be completely wrong. There are two parts. We have an electrochemical part that turns this molecule from neutral to charged. But when it turns charged, it's not because of an electrostatic energy that does this. It has to do with very subtle chemistry with this nitrile group, nitrogen and oxygen, and splitting OH, H2O into OH minus. And so I don't want to go into it, but there's this thing called a side reaction. So here's our molecule. We oxidize it, and then it's charged. We thought this charged molecule would be polarizing things. It doesn't. But we also found that it self-discharged and went back. That's a problem because it takes energy to oxidize the molecule. But on the way back, if it grabs the electron back, you recover it. So it looks like we could recover all the energy, but for this self-discharge reaction, we now understand this. We think we have a solution, remains to be seen. I'm not going to go into this, but I just want to conclude, leave 10 minutes, is that I do feel like an E. coli. Now, I learned about E. coli from Ed Purcell, who invented NMR and did the first scanning of the hydrogen clouds in our galaxy. And he said that this thing will swim, and it's too small, so it swims and it measures changes by its motion of it's going for food. So these things want to eat food, and then they split. And so it will go swim, tumble around, and swim again. If it feels the gradient is going towards food, it keeps on going. But if it doesn't see any gradient, it doesn't stop and just sit there waiting for a signal. It just continues to swim. So it's like the perfect graduate student. You always swim towards progress, but even if you don't feel that you're making progress, keep on swimming. Anyway, that's this random walk of E. coli, and that's my life. Thank you.
Well, thank you. It's a fascinating story, which we should learn. So, any questions from the floor? Yeah. There.
Thank you so much for this wonderful journey. I was wondering, since you have been part of, like the government as the Secretary of Energy, but also for private institutions like the Bell Labs, as well as universities, I was wondering, since you're tackling such a huge issue such as climate change, what is policy-wise, or like maybe even like a moonshot-wise, like the bottleneck, and how can you best approach this problem? Is it scalability? Is it basic science? Is it all of that, or what is currently the status of that?
Yeah, great question. When I left the department, I went around started to talk to rich people to say what we really need is roughly akin to a Manhattan Project, but a Bell Labs for energy. Okay, in Manhattan Project, you're single use, you don't care about money, you don't care about anything, you want to make a really expensive bomb because you're at war. This is different. The solution has to be economically viable, and so you need something that makes economic sense. Remember Sheikh Ahmadi, it's got to make economic sense, but it's going to be basic research, it's going to be applied research, it's going to be all of the above. And I said, we need a Bell Labs for energy. And I was told, nah, rich people give to their alma maters, but they may not give to this, by a couple of rich people. So I gave up. I still think we need a Bell Labs for energy. Now, whether the U.S. government's going to help, well, it may not for the next three and three-quarter years, but eventually I would hope that the U.S. government, the European government, the Chinese government, all these people, because this is something, even though there's going to be valuable intellectual property, it's too an important problem. And we need the best minds rowing together.
Thank you so much.
Yeah. Second.
Thank you for giving me the opportunity. I'm not a scientist, I'm a historian of science and technology. And as a Chinese, I'm quite proud that you and Professor Samuel Ting are separately the fifth and the third Chinese American who got the Nobel Prize. So I wonder, how do you think of the traditional Chinese culture and family cultures on the steps to your success in science? And,
Well,
thank you.
as you know, the Chinese put a huge value in education in general throughout all society. My family was a personal extreme of that. I was told when I was like in the second grade, my father said, you know, Stephen, don't get married until you get your PhD. It was assumed that we get a PhD in science. And so, by the way, you younger people have kids, don't do that to your kids. Let them do what they want to do, encourage them. But I think the tradition and the seriousness of education and the fact that it is considered really to be a scholar is one of the when I was growing up, to be a scholar was the highest achievement you can be. Not a head of a company, not making a lot of money, not being the boss of anything, being a scholar. And I was told that. I still believe that. Which is why I didn't want to take any bureaucratic job. But sometimes one is willing to take a bureaucratic job because it actually gives you leverage if you can inspire people to go in this direction. But the short answer to your question is very much in my blood, in my DNA as a Chinese American.
Okay, thanks. Other questions? Yeah.
Somewhere back there, I can't tell. Oh.
So thanks for the talk. It's very inspiring. But I think you are very modest in calling it random walk, random changes. I think in my mind, and maybe you can reflect on it, doing science and looking at science doesn't matter what you do, what your discipline is, what you want to advance, and what you are curious about. It requires two kinds of being smart. You have to be academically, scholarly, curious-wise smart, but you also have to be street smart. And the street smart is the moves that you probably try to make. And actually, I think you were guided by street smartness, and then you got this thing. So I'm kind of confronting your assumption that it's random. It's not really random, in my mind.
Okay.
You are being modest, of course, saying, "Oh, I was just walking there. I drank wine and I moved left and right." No, I think it's street smartness. Can you reflect on this?
Well, okay. So I have wide-ranging curiosity, but I would not know very much about anything. And so what I found was that, piqued by this curiosity, then I start to dig. And for example, in the curiosity about climate change, I started digging. I wasn't going to talk about climate change until I really understood the literature. And I started teaching classes on the physics of climate change so that I became an expert, so I wouldn't just spout off like, a Nobel laureate. And what Sam Ting said was very wise advice. He said, you don't talk about things you don't understand, but that doesn't prevent you from actually getting very deeply into an understanding. So this wide-ranging, know a little bit, oh, that looks interesting, scratch a little, dig a little. Oh, and then the next thing I would do before spending a lot of time, I'd go find some expert and say, I'm thinking of doing this. Is this stupid, crazy? Sometimes they said, nah, it's great, except it's done 5 years ago. Other times they said, nah, it's not going to work because of this, and we'd haggle about it. And maybe 5 or 10% of the time, I said, yeah, sounds like a good idea, try it. So I didn't waste a lot of time in the library. I talked to people immediately. I got in the habit of doing that when I was a graduate student postdoc, and really got good at it at Bell Laboratories because there's so many experts walking around. And so again, my advice to young people, do it that way. Don't hide in a library, or now you don't, you ChatGPT it. But if you ChatGPT it, don't believe much of what it says. Use it as a pre-Google, but eventually go and talk to an expert before you read a lot of papers. Then you can have really targeted reading.
Any other questions from maybe from students?
Very bashful students. No? Okay.
Okay, if not, let's thank the speaker. Great talk.
Thank you.